From this lecture, we will start a new chapter, that is field effect transistors, and in this lecture, I will give a small introduction about the field effect transistors. I will give a small introduction about the field effect transistors. We will try to understand what are FETs and also compare them with BJTs. We will compare FETs with bipolar junction transistors. So this is what we will do in this lecture. Now we will move to the first point, and in this point we will talk about terminals. We already know BJT is a 3-terminal device. BJT is a 3-terminal device, and like BJT, FET is also a 3-terminal device. FET is also a 3-terminal device. In this figure, you can see the first box is representing the BJT and the second box is representing the FET. And in case of BJT, we have 3 terminals. This terminal is the base terminal, this terminal is the collector terminal, and this terminal is the emitter terminal. The current IB is the input current, and the current IC is the output current in case of BJT. And in case of FET, this terminal here is the gate terminal, this terminal is the drain terminal, this terminal here is the source terminal, and the potential difference between these two terminals is equal to VGS, V subscript GS. This is the potential difference between the gate terminal and the source terminal, and the current in this branch, that is the output current, is equal to I subscript D. So BJT and FET both are 3-terminal devices. Now we will talk about applications. To a larger extent, the application of FET is same as application of BJT. The application of FET is nearly same as application of BJT. So we are done with the first point. Now we will move to the second point, and in this point we will talk about what type of device is FET. BJT is current control device. You can see here the output current is IC, and IC is equal to beta times IB, where IB is the input current. So the output current is dependent on the input current. So we say BJT is a current controlled device. On the other hand, the current ID is dependent on the voltage VGS. So FET is a voltage controlled device, and this is the main difference between BJT and FET. BJT is a current control device and FET is a voltage control device. IC is a function of current IB. Current IC is the function of input current IB. On the other hand, in case of FET, current ID is the function of voltage VGS. And you can see in both the cases, the output currents are the functions of input parameters. So we can say that the output currents in both the cases are controlled by parameters of input circuit. VGS is the input voltage in case of FET, and IB is the input current in case of BJT. So we are done with the second point, which is very important point, because this is the main difference between BJT and FET. Let's discuss the third point. If you remember the first presentation on BJT, then I told you BJT is a bipolar device. BJT is a bipolar device, and this word bipolar is reflected in the name BJT. B stands for bipolar. On the other hand, the field effect transistor is unipolar. This means FET depends solely on either electrons or holes. So FET is a unipolar device because it depends either on electrons or on holes. So this is all for the third point. Now we will move to the fourth point. And in case of FET, we have N-channel FET and P-channel FET, P-channel FET, like NPN transistor and PNP transistor. When the FET is dependent on electrons only, then we call the FET N-channel FET, and when FET depends only on holes, we call that FET P-channel FET. FET can be used for amplification as well as switching. The fourth point is FET can be used for amplification and also for switching. Like BJT, we can use FET for amplification and for switching. Let's move to the fifth point, and the fifth point is related to the hierarchy we are going to follow in this chapter. The field effect transistors can be broadly classified into two types. The first one is JFET, the junction field effect transistor, and the second one is MOSFET, metal oxide semiconductor field effect transistor. In this chapter, we have to focus on these two field effect transistors. We can further classify JFET into two types. The first one is N-channel JFET and the second one is P-channel JFET. Classify into two types. The first one is D-MOSFET, and the second one is E-MOSFET. And again, we can classify D-MOSFET into two types, N-channel, P-channel. E-MOSFET we can classify into two types, N-channel and P-channel. So this is all about the hierarchy we are going to follow in this chapter. Now let's talk about the history of field effect transistors. This is the sixth point, the history of field effect transistors. The field effect transistor was first patented by Julius Edgar Lilienfeld. Julius Edgar Lilienfeld in 1926 and by Oscar Hale in 1934. And these patents were not for the actual FET but for the concepts and FET-like devices. In 1947, William Shockley and his team tried to make a FET but failed. While they were trying to diagnose the reasons for failures, they discovered the first transistor or point contact transistor. And after 1 decade, the first JFET was made. And MOSFET, which is better than JFET, was invented by D. Kong in 1959. So this was the history of field effect transistors. Now we will move to the next point, and in this point we will try to understand meaning of field effect, in the name field effect transistor. In case of field effect transistors, an electric field is developed by the charges present. An electric field is developed by the charges present, and this electric field controls the conduction path of the output circuit. This electric field controls the conduction path of the output circuit. So there is an effect due to electric field, and because of this reason we call the device field effect transistor. Now let's move to the next point, and in this point we will talk about input impedance. Field effect transistors have high input impedance as compared to BJTs. In the next point we will talk about temperature stability. FETs are more temperature stable. FETs are more temperature stable as compared to BJTs. In the next point, we will talk about area occupied or the size of FETs. Field effect transistors are smaller than bipolar junction transistors. The last point is related to sensitivity. BJTs are more sensitive to the applied signal as compared to the FETs. So this is all for this lecture. If you have any doubt, you may ask in the comment section. In the last presentation, we saw the introduction of field effect transistors, and the first field effect transistor we have to study is junction field effect transistor, popularly known as JFET, where JFET is the ability is p-channel JFET. In this lecture, we will see the construction and working of n-channel JFET. If you remember the BJT lectures, we used N, P and BJT to understand the concepts and problems. Now while discussing JFET, we will use n-channel JFET. You can see the construction and the major part of JFET structure is n-type material. You can see the major part of the structure is n-type material, and it is forming a channel between two embedded p-type materials. We have two p-type materials, and this n-type material is forming a channel between these two p-type materials, and because of this reason we call this structure n-channel JFET, because n-type material is forming a channel between two p-type materials. And when you see the construction of p-channel JFET, you will find p-type material is forming channel between two n-type materials. You can see 4 ohmic contacts in this structure. This is the first ohmic contact, and this terminal is the drain terminal. The drain terminal represented by capital D. The second ohmic contact is this one, and the terminal here is the source terminal represented by capital S. The third and fourth ohmic contacts are connected together, and one common terminal is taken out, which is called as gate. This is the gate terminal represented by capital G. JFET is a 3-terminal device. Like BJT, JFET is also a 3-terminal device, and when you see the physical structure of JFET, you will find it is like BJT. When you see the physical JFET, you will find it is having 3 legs like BJT, and the construction is same as BJT. In case of junction field effect transistors, there are 2 PN junctions. The first PN junction is formed between this p-type material and the n-type material, and the second PN junction is formed between this p-type material and the n-type material. And because of this we have two depletion regions. Two depletion regions are formed at 2 PN junctions. The pink portion in the construction is the depletion region or depletion layer, and we already know depletion region is depleted of free charge carriers. There are no free charge carriers in the depletion region, so it will not help us in conduction. And if you increase the width of depletion region, like this, then width of n channel will reduce, and because of this there will be obstruction in the flow of electrons. When you connect drain and source terminals to a potential difference, then because of this potential difference the free electrons in the n channel will be drifted like this, and the conventional current ID will flow like this. But if you increase the width of depletion region, the flow of electrons will be obstructed, and we can control the width of depletion region using the gate terminal. So we can control constructed, and we can control the width of depletion region using the gate terminal. So we can control the flow of electrons by using the gate terminal. The potential difference between the gate terminal and the source terminal will control the width of depletion region, and this potential difference VGS will now control the output current ID. So we call this device voltage controlled device. BJT is a current controlled device, and if we talk about working of BJT and working of JFET, then working of JFET is very easy to understand. The working of BJT is little bit complicated as compared to the working of JFET, and from this explanation you now have some idea about the working of JFET. But before moving to the complete explanation, I will first try to explain one simple analogy. To understand the working of JFET, we will try to understand the working of spigot. You can see spigot on your screen. It is also called as tap. This knob here is called as valve knob. The water is coming out of spigot from the overhead tank. We have the overhead tank, and the water from overhead tank is coming out of spigot, and here we have the drain. This is the drain, or you can say the sink. Now let us try to compare the working of JFET with the working of spigot. Water is coming out of spigot because of potential difference. The potential of this stored water is the reason for the water coming out of spigot. So we can say that the cause of water flow, in case of spigot is same as the applied voltage between the drain and source. The applied voltage between drain and source, because when you apply voltage between drain and source, the electron in the n channel will drift, and water is same as electron in the n channel. The next comparison is between the valve knob and the gate. Here the valve knob is controlling the water coming out of spigot, and here the gate is controlling the movement of electron in the n channel. So we can say that valve knob is same as the gate in JFET. The next comparison is between the sink and the drain. The sink in this case is same as the drain in case of JFET. You can see water is going in the sink, and here electron is going towards the drain. So their working is similar. The next comparison is between the source in case of JFET and the source of water in case of spigot. The source of water is definitely the tank, the overhead tank, but if you see only this portion, then you will find the source of water. This is water. The source of water is nothing but the spigot. So source of water is spigot, and this water is going to the sink, which is working like drain. So spigot is working like source in case of JFET. So I hope you now understand this simple analogy, and if you have any doubt, you may ask in the comment section. In the next